Welcome everyone, and I'd like to introduce you to a simulation model built in Excel. We'll call it Flow Simulator version 0.15, as you can see on the top here, so pretty early version of this tool. But what I'd like to do in this video is just show you some of the basic features, how the data gets in, what some of the outputs are. And then in another video, we'll actually go through an example and run the model and make changes to it and see how we could use this as a process improvement tool or a line design improvement tool. So basic background, the Flow Simulator version 0.15 XLSM is the engine file and also shows the results of running a simulation model. And the data will be stored in a separate file. In this case, it's called Workshop Simulation Model, but you could have many different data files and just point to the data file that you want to use. And then, of course, the tool will pull in the data and run it. Now, background. What are we looking at here? Well, we're looking at a manufacturing assembly line or line, and the source data for this model came from a couple places. One is this one. This is an example of what we call process flow diagrams, and we're labeling different models that share these similar paths. So in this case over here, DR12, DR54, DR11 share this kind of structure, flow path. SD04 has this one, these three have this one, and so on. So we have an idea of the actual process flow for each of the models that we want to simulate. The other input information is this worksheet here, which contains all the process times for machine and labor when those two exist. Processes are across the top, machine and labor, and then the process times all expressed in minutes, and the process volumes. So this was the worksheet that we used to actually calculate initial takt time, number of resources, and create this initial layout. And the purpose of this simulation tool is just to validate that initial design. Remember, this is a static calculation that we're looking at here, but what we'd like to do is test this in the real world, so to speak, testing the flow, testing the relationships of processes and the times, to make sure that before we invest time and energy into the physical implementation of this line, that we have something that's going to work for us. So a couple of the worksheets that we have in this model that are used as inputs: flow description. This is a slightly different way of viewing the process flow diagrams. Each one of these codes here describes a linear set of work steps or linear set of processes. And in examining the process flow diagrams, we were able to break it down to 5 different linear flows. FIN, F-I-N, is final assembly, which includes wiring. FIN 1 includes final assembly without wiring, mandrel, molding, and motor. So this describes all of these potential pathways, but in a linear format. So each of these is one step after another. Now, resources, these are all the possible locations. These resources could be either workstations, like you see here. Here's FIN 1, so Final Assembly Workstation 1. So that would be a location where a person would do work. Or ELE, electrical test, is an electrical test workstation. Down here at the bottom, we have operator 1, 2, 3, 4, up through 7. So we have a resource which is a worker, a human being. And then we have this thing we call an IPK, so quite a few of those. An IPK stands for In-Process Kanban. That is a buffer. That is a space that allows one piece to be placed into. So IPKs typically after each of the processes is shown here, and those are also resources that we want to track and monitor. So here's a complete list of our line layout, and if you looked at the final layout of our line design, you'll see one of these as a little box or an indicator on that layout. Now, the flow relationship is what's sometimes called a routing, or we're calling a process flow diagram. So what you're seeing here on this screen is an actual explosion of these 5 codes under flow. So, for example, molding is molding to, over here, molding IPK, and molding IPK goes to GRI, which is grind, and then grind connects to grind IPK, and then grind IPK connects to FIN 1. So it's a linear relationship, and it describes all the steps, IPKs and workstations, from mold all the way to consumption in the final assembly line at workstation number 1, and so on and so forth. So each of those 5 flows are described here in a linear fashion, documented. Also, there's room here to specify how many units are produced from each input unit. For example, we could have 1 input and 4 outputs, and then number assembled in the next step, what's the quantity there, etc., etc. So there's room for some amplifying of this information. How many operators work at each step, and which operator code, operator 1, 2, 3, 4, 5, etc. So we complete this table. Here are the products that we're building. All of these, DR11, 12, 13, are the actual end items in our sample line. And then we have what are typically called subassemblies. So we have mandrel subassembly, we have molding subassembly, and we have, well, that's it, mandrel and molding. So we're consuming these subassemblies into the final assembly, and these items here are what we're actually delivering to our customers. Now, the sequence is what we're actually building, what the order of production. So what you see here are a list of those end item products, the subassemblies that are required. You notice not every subassembly is required for every unit. So this is like a bill of material you see here. And then how many units are produced. So starting at line 2, the simulator is going to take this first product, DR12, and produce 10 units of that one. Then it's going to go to the next one, also the required number of subassemblies. Then it's going to go to DR54 and run that one, etc. So this could be as detailed or as high level or as batch oriented or as single piece flow as you like, but it's the instructions the simulator is going to use to actually execute and run. Now, process times, this is important. For every single product and process, so OS31 is the product and electrical test is the code, we have a time for machine and a time for labor. And those times would come from standard work definitions or time studies you've done, but this is going to be critically important as well. So it's quite a long list, but every product/process has a time. And this is what you saw here. Every product along here and every process across the top will have a time if it's used, if that process is needed for that product. So that's where the process times come from. It's just more in a linear format rather than a matrix kind of table. We also have times for travel. So between each of these resources, between the workstation and the IPK, between the IPK and the workstation, there's an option to put in a travel time or a move time. And that's important because that move time is going to be added to your cycle time. It's time that you're consuming, even though you're not actually working on the product. So it's important to know that. Or it can be set, if it's relatively small, it can be set to a very small number. But we're actually able to track and record and add that time in to our analysis. So that's it. That's all the inputs we need. And so we go back to our flow simulator, and here's how we run it. We go to Add In. This is Excel, remember. Kaplan BG, Kaplan Business Group, is the developer of this tool, kaplanbg.com. You can look them up. They're a San Diego-based industrial engineering and consulting company. And we just click on this button, Simulate. So Simulate opens a window, and we're ready to go. What you see here is a kind of a crude layout of the line, but there is an option you can see here for graphics. You can upload a picture of your proposed layout and then overlay these symbols, these icons on top of them. And we're going to use this to animate the flow of work. The data file lets you select the file that you want to execute, the one we just looked at. Warm-up time is run the model for a certain number of minutes and basically load the model with work before you start collecting data. Otherwise, it starts as an empty line and takes some time to fill up. And then the runtime, collect data for this number of minutes, or until you run out of orders on that list of orders file. Enabling animation. If we turn animation on, it allows us to track individual orders, and there's a color code system that lets us know if it's busy or idle or blocked or moving or waiting with a color code. However, turning animation on does slow things down because the system has to update all of the icons continually. So that's about it. You can run it with animation enabled or disabled, but let's go ahead and run it briefly, and we'll show you how this works. I'll turn it on, so animation's enabled, and run. It takes a few seconds for the data to be pulled into memory, and then the model starts to run. And we can slow this animation down if you want to track very carefully, especially for debugging the model. Otherwise, you can just let it run. We see up here the time. So we're at 43, 44, 45, 46. These are simulation minutes. It's going to run to 425, remember. Now watch what happens when I turn animation off. I disable animation, and it's going to speed up tremendously. For 435 simulation minutes, it's going to be able to execute that in about 15 seconds or so. So usually once you're confident the model's working the way you want it to work, then you turn the animation off. And there we are. So in this model, it gives us a summary of results. We ran for 135 minutes, the warm-up time was 30 minutes, and we completed 229 orders during that time. Now that's not a real good result for us, I'll have to share with you, because we designed this to run over 456 units to be precise. So there's some analysis we'll have to do here to figure out why those results are so low. There could be a number of reasons. One might be just a bug in the data that we entered. It's just some bad data that we can correct. But the other thing is just basically our line design and the variability of work content time and how things are interacting prevent us from reaching that number. So this is the beauty of the simulation tool. We can use it to run different scenarios, test different production sequences, or look at the times, look at the layout, add resources, all of those good things to get this design to where we want it and need it to be. This is so much more beneficial than doing it once the line's already in place, when making changes may be possible, but a lot more expensive. So that's it for this demo. We'll follow up with another video actually following through an example where we can see changes being made to the data model. Then we'll re-execute and follow, for a few steps at least, our progress in making improvements to this line design.